Good morning, everyone. Thank you very much for tuning in yesterday. And today, once again, we have Mr. Dhanaraj with us to share with you some technical knowledge on flow assurance, specifically in terms of wax management. Thank you, Mr. Dhanaraj, for actually spending so much of your precious time and weekend with us. Without further delay, let's welcome Mr. Dhanaraj once again to share some insights on flow assurance.
All right. Thank you, Arvind. Good morning, everyone. Today I will be talking about flow assurance on wax. So, without further ado, let's continue with the presentation. Let me share my screen. All right. All right. So, the objective for today's presentation would be to provide an overview on wax to petroleum engineers, especially, and it is intended that audience will reach at least awareness level in wax. Okay, let's look at what is wax all about, the definition and also the meaning. As you are aware, in your reservoir fluid consists of paraffins, naphthanates, aromatics, saturates, and also your resins. So the property that actually contributes to the nature, the waxy crude nature of your crude is actually your N paraffins, which is your higher molecular weight straight chain alkanes. That is N17 and higher. It is known as normal paraffins that precipitates from your reservoir fluid when your fluid temperature reaches wax appearance temperature. As you can see from this diagram here, this is actually a gel, and this is actually wax plus scale that is being deposited on the pipe wall. So when your fluid temperature reaches a temperature which is called the pour point, your wax will form a kind of a gelation solid that will gel up the whole flow line. And as you can see here, this is due to the cross sectional area of your flow line has decreased due to the wax being deposited on your inner pipe wall. And this is considered a hard wax, as it is a combination of wax and also scale at the same time. So it is impossible to pick this line due to the hard nature of the wax that is formed. The reason why this hard wax has formed is because most probably they did not pick frequently. So basically your wax tends to get your wax age, and it tends to get hard. And at the same time, you have formation water as well in your flow line, and your formation water consists of scales. So it combines with your scales, and it forms a hard wax in your pipeline. So how does wax form in your fluid? When your fluid temperature is above W80 or wax appearance temperature, your wax molecules are actually dissolved in your oil. And when your fluid temperature reaches W80 or crosses W80, W80 is wax appearance temperature, solubility reduces. So the wax molecule will start to precipitate out from your fluid, and it will start to crystallize. And deposition will only form when there is the temperature difference between your bulk, and also there's a temperature between your bulk fluid and the environment. So basically, if your fluid temperature is the same as your environment temperature or your ambient temperature, therefore deposition will not occur, and the wax that is being crystallized will be transported as a slurry instead. It will not be deposited on a pipe wall. And if you look at this formula here, this equation is actually derived from Fick's law. So your deposition rate is highly dependent on your concentration gradient and also your temperature gradient here. So your driving force here is your temperature gradient. If there is no temperature gradient between the bulk and also the ambient condition. Therefore, dt over dr will be 0. When this is 0, there won't be any deposition of wax on the inner pipe wall. As the temperature decrease further to the pour point, this is when your viscosity will increase sharply and wax crystallize interlink to form a matrix. This is when the whole pipeline will be gelled up, and this situation is called gelling. All right. So let's look at the what wax can actually increase the pressure drop across your flow line. Since it reduces the flow area, it changes the pipe wall friction and increases the fluid viscosity, especially when fluid reaches the WAT. Below WAT, your fluid will tend to be, it will behave as a non-Newtonian fluid, where it is highly dependent on shear. So this phenomena or behavior is called a shear thinning behavior, and it can cause emulsion to form. All right, and it can increase the tendency for a pick to get stuck when you don't frequently pick your flow line. All right, we need to maintain the pressure drop across at least below below 3 bar. If it is more than 3 bar across the peak, then you might face a peak getting stuck in your pipeline. So this will cause production stoppage, and to remove the peak, you need to you may need to cut the pipeline. All right, and at the same time, it can increase tendency for instruments to fail, and also we also may face a production stoppage and facility modification, and instrument need to be replaced. So, and if it is temperature goes below your pour point of your fluid, your pipeline may get plugged with a gel, and this will then we need to replace the whole pipeline. If it is an offshore pipeline, then yes, once your pipeline is gelled, the whole section of your pipeline is gelled by wax, then you may need to abandon the pipeline and replace with a new one. Okay, if it is onshore, then there's a way of saving your pipeline. I will show you. I will show a case study later. It's in one of the oil field in Africa. So I was actually attached to this project, and they also faced this particular issue where the whole pipeline got gelled because they did not pick the pipeline frequently. All right, it is a very highly waxy field. And as you can see, this is a typical phase envelope of your fluid and also your wax. So this is your phase envelope of your fluid, all right? And this is here will be two phase. This will be liquid, and this will be your vapor, and this is your critical point, right? So there's a solid phase here, which is called your wax phase envelope. This is your wax phase envelope. Basically, as your fluid, if your fluid operates here, you will have a wax being precipitated. If it is outside here, wax will not precipitate. So you not face any issue on wax here, right? If you're operating in these conditions. How do we predict this particular line? And this particular line can be predicted using a software, a thermodynamic software, all right? And it is predicted using a special equation of state model, all right? The commercial software that we use to predict this wax is actually, like, for example, PVT sim and multi-flash, all right? So we need this line and to be predicted, and also the wax precipitation curve to be predicted as well, and also the viscosity below WAT need to be also predicted, and we need to match the viscosity below WAT against the laboratory data. Yep. And if you notice that if it is operating below your below your bubble, this is your bubble point. This is bubble point line, and this is your dew point line. So if you were to operate below bubble point, so basically you have two phase here. You have a mixture of gas and also liquid. So the gas and liquid will actually give kind of an inhibition property to your fluid, whereby you can see that your wax precipitation or your wax phase envelope will tend to move away, or will tend to move towards the left hand side. So there's a curve here. So basically, if you have a solution gas in your fluid, it will help the wax issue. All right. So injecting condensate or injecting gas into a waxy crude can help uh, the wax issue. However, we may need to check on asphaltenes. All right. If we were to mix gas and oil into a gas and oil, asphaltene will be an issue, because that's when asphaltene will start to destabilize and will start to precipitate. Unlike wax, at least wax we can it is a reversible formation, is a reversible process, whereby we can at least melt and recover the oil. All right. However, asphaltene, once it's formed, it will stay in your production flow line and also in your separators. So it's a solid, and it may cause plugging to your valve bores or to your flow line, or it can clog your pump scrubbers or pump filters, or yep. So, but most like asphaltene is an issue because it's an issue if it is in valve bore. But topside we will not face any much asphaltene issue unless we are mixing with gas, oil and gas. So that part of it we need to check in the laboratory on the asphaltene severity as well. All right. Besides wax also, yeah. If we were to mix condensate or oil together. All right. Now, these are some of the basic properties and measurement that we can actually quantify, or we can quantify for in terms of amount of wax, or the properties that contribute to your waxy behavior of your crude. So the first is we need the C36 compositional analysis done on your dead fluid, which is your stock tank oil, and then the end paraffin fraction, which is your NC17 plus of your crude, your wax appearance temperature, WAT, which can be measured using cross polar microscopy or differential scanning calorimetry. Your pour point and your wax content, right? But your wax content, preferably if you are doing a modeling for your wax, we will not match against the wax content. This is much more, your end paraffin fraction is much more accurate in terms of the amount of wax, all right? In terms of measuring the amount of wax. So this gives a better accurate measurement as compared to the wax content. So we will depend on the end paraffin fraction in matching the properties of your wax in the thermodynamic modeling, all right? So viscosity, we need at least three different set of data on viscosity at three different shear rates. So shear rates here can be, it's actually your can be also known as your flow rate. So basically, how do we identify the shear rate is depending on the flow rate of your flow line. So in the lab, we need to mention to the lab people that we need to specify this to the lab people to conduct at three different shear rate. But then, and these particular numbers must be consistent with the flow rates in your flow line. so that we can have a better measurement in terms of the viscosity and also in terms of the prediction later on when we're doing the modeling. All right. And the deposition rate of or deposition tendency need to be also measured. All right, this can be measured through mini flow loop or cold finger test, or we can also measure it again using operational data amount based on the amount of wax being removed by a pig for every 2 weeks, or for every pigging cycle or pigging activity. So there's three ways of modeling or predicting the deposition rate. All right. So we need this deposition rate uh, because we need to tune the diffusion coefficient of your wax model. If you notice earlier, I've shown this formula. So this is derived from Fick's law, as I mentioned earlier, and there's more to it actually, but this is just a very brief equation. So this property here, this is your diffusion coefficient that we need to tune. All right, based on the cold finger data or from the mini flow loop, okay, data, or from the operation data. This is what we need to tune. All right, so that we get a better measurement in terms of the wax deposition rate. And this is predicted using the simulation. No, sorry, predicted using thermodynamic software, the DC over DT, and it is highly dependent on your, as I mentioned earlier, it is highly dependent on your end paraffin fraction, right? And your DT over DR is actually your temperature gradient um, between the bulk and also ambient, and this is predicted using the Olga modeling. All right. So as you solve this equation here, you be able to um, get the deposition rate, and in turn you can calculate or can, and in turn you can also obtain the results of the thickness of wax across the flow line in your pipeline simulation software. Okay. So moving on. Next, we can also, yeah, we need the gel strength, because we need this gel strength will give you the properties of your when your wax or your fluid goes below pour point. All right. And when your wax tend to gel up, so when wax tend to gel up, so we need to measure the strength of the wax, because strength of the gel. We need to because we need to compute the gel breaking pressure later on. So this property is also need to be obtained in the lab, from the lab. And impact of emulsion and also impact of inhibitors, but this is not really crucial or critical. Some labs do it. It depends on the client whether they need this measurement done in the lab or not. All right. So all this measurement, client as in operating companies will approach laboratory and request the laboratory to conduct all this analysis for the wax. All right. We as like myself, as a consultant, we will just conduct the simulation and do the modeling for the wax. All right. So, but in terms of the wax characterization will be done by the operating companies. They will characterize the wax based on the lab. So the engineers will characterize the wax based on the lab, and will provide the fluid, the waxy fluid, to consultant, and consultant will do the simulations for the wax. All right, wax simulation. Okay, there's two terms here, which is a cloud point and WAT. All right, cloud point is actually is a temperature at which the crystal starts to appear and form a kind of a cloudiness appearance in the sample. All right, that's called cloud point. But we will not use this measurement to tune the wax model. All right, we use the wax appearance temperature measurement to, and this is actually the temperature at which the first crystal is formed, at equilibrium with dissolved, and it is at equilibrium with dissolved wax. So I'm not sure everyone is able to see this, but so this is how we measure WAT visually, is through cross polar microscopy. So we need to conduct few measurements and get an average value of all those measurements, because there's a lot of human error as well involved, because everyone has a different site. So basically we need to take few measurements, and also few measurements, and we need to get an average, or take the most conservative value in terms of the WAT. All right. But the most accurate measurement would be through the differential scanning calorimeter metry. Sorry, calorimetry. So it is depend on the um, sol- latent heat of solidification of your wax. As you can see here, as you cool down your fluid and it reaches the onset here, so at this temperature, you can see that there's a latent heat of there's a spike in the heat that is being emitted. Okay, this spike in heat is actually showing that the nature of exothermic nature of your at this particular uh, temperature, whereby when solid wax is formed, heat will be released, and this is a exothermic process. And exothermic process, that as you can see, the heat that is being released is called the latent heat of solidification, or it's known as a latent heat of fusion. So the temperature difference, or there won't be any much that temperature difference at this region, that due to the change in phase, all right, from liquid to solid. That's the reason why the temperature difference is very small, because when during change phase change from liquid to solid, there will not be any temperature difference. All right, and it is an exothermic process. So this here will be your WAT, and at this temperature, so we can obtain two data from here: the WAT and also the disappearance temperature. So wax disappearance temperature, as you heat it up again, and this is your onset of your WDT, wax disappearance temperature. So your WAT is 11.87 and your WDT is about 13.69 here. Yeah. Another measurement we need is actually your pour point, okay? Because we do not want to operate below pour point or near pour point region, because as you operate your flow line at pour point, then you will have a gel formation, okay? Your gel formation across your flow line. But this is done on dead crude, not on live crude. So basically, the measurement of your pour point in your lab is very conservative, all right? Because if you are operating if it's like a live fluid where you have a solution gas, then your pour point might be even lower than the measurement, because your solution gas itself uh, helps to inhibit the pour point as well, all right, to decrease the pour point. So this measurement can be done. It is quite a simple measurement, just that simple measurement whereby they just reduce the temperature of the fluid, and observe when the fluid cease to flow. When the fluid cease to flow, that's when they that's when the temperature they will obtain that particular temperature, and that temperature will be known as the pour point of your crude. And this is one of the most important measurement for wax, which is your end paraffin distribution data, that it can be obtained through HTCC, high temperature gas chromatography. we need this data and peripheral distribution in order to compute or to measure or to obtain the wax fraction. So the wax fraction is very important because that will determine the amount of wax that can deposit in your pipeline. All right. This property is very important to be conducted, or this property is very important to be measured in the lab. Right. And we need at least we need end-period distribution at carbon number as high as possible with sensitivity level up to 1 parts per million. Okay, so at a very so we need at a higher carbon number, right? At least 1 ppm. If not, or else we need to extend it through mathematically in a spreadsheet, and we need to extend the distribution to 1 ppm through through calculations. So because this one will contribute to the first wax crystal. So basically, we need to extend it to 1 ppm because that will actually affect the WAT prediction later on. So it's important that we extend it to 1 ppm. So another measurement is your wax content. So this wax content is actually just used as an indicative measurement on the amount of wax, and the quantity, this particular quantity should not be used for your modeling. So we need to use the HTGC instead, the end paraffin HTGC measurements, all right, in order to calculate the wax fraction. Okay, let's look at viscosity below WAT. So laboratory need to measure the viscosity below WAT at least at 3 different shear rate and at least at 2 different cooling rate as well, because at a faster cooling rate your fluid cool faster and therefore it is less viscous. For faster cooling rate it is more viscous, but it depends. Some lab will conduct, some client will request to conduct 2 cooling rate, but some client will request just one. It depends on the pipeline, how insulated is your pipeline is. If your pipeline is insulated, then of course your cooling rate we will just measure for 1 cooling rate, which is a slower cooling rate. For if the pipeline, your particular pipeline is uninsulated pipeline, then we need to measure at a higher cooling rate. All right, for in terms of the viscosity measurement. Okay. As I mentioned earlier, so your fluid above WAT will behave as a Newtonian fluid. All right, Newtonian fluid means it does not depend on shear, and as the temperature decreases and reaches to a point where there is a sudden spike in your dynamic viscosity, that's when your fluid will behave as a non-Newtonian, will have a non-Newtonian behavior, where your viscosity increases sharply here at this point. If you notice here, at this is also one of the measurements. At a higher shear rate, your viscosity is lower. At a higher shear rate, your viscosity below WAT is lower as compared to at lower shear rate. Okay. At higher shear rate, your crystals are smaller. All right, crystals are smaller, so it will be less viscous as compared to operating at a lower shear rate. When you have low shear rate, then your crystals are larger, so viscosity will be larger as compared to operating at a higher shear rate. So below WAT, it will be highly shear dependent. Highly shear dependent. You see, at above WAT, it is not your viscosity is not dependent on shear. Only below WAT. So this behavior here is called a shear thinning behavior. All right. And in modeling in modeling, we need to obtain the DEF constant here in your thermodynamic software when we we are trying to match the viscosity below WAT. So this coefficient or these constants are important because we need those constants in your Olga run, all right, to obtain a accurate prediction for accurate prediction of viscosity in your pipeline at different temperatures, right? At different temperatures, and also at different shear, right? So let's look at the deposition rate measurement. Okay, for deposition rate measurement, as I mentioned earlier, we can actually measure through cold finger data using cold finger, which is this, and also through mini flow loop. So mini flow loop is much costly compared to the cold finger data, the cold finger measurement. So how does a cold finger measurement looks like is, if you see this is your finger, all right, and then this will be a cold fluid. Cold fluid will be inserted inside. Will be channeled into this finger, and there's a cup here with agitator here. There's an agitator here. So and this is set at different RPM. So this will give shearing in your fluid, and inside your cup is filled with oil, all right, your waxy oil or your dead oil, dead crude. Outside it's water, and then it is being warmed by heating element. So as you can see, your cold finger will be cool, and your oil is actually being warmed up by the hot water. So it's being heated up by the water bath here, hot water bath. So since there's a temperature difference between this two between the oil and also the cold fluid here, therefore the wax will start to precipitate on the finger, right? And we need to we need to apply certain shear in the fluid, all right, and this depends on the flow rate of your pipeline, all right. So we need to make sure that we match the shear in the pipeline so that we can get an identical measurement in terms of amount of wax being deposited on the finger. So once we do this conduct this experiment, we need to obtain the amount of wax being deposited on this cold finger, or the wax mass flux for a certain duration. All right. So we need that data later on to tune the diffusion coefficient, which I've shown earlier. So in terms of wax models, there are two parts. All right. One is your thermodynamic modeling, which is your wax precipitation curve that I've shown, which will look like this. This is your wax precipitation curve that need to be predicted in your thermodynamic software or through PVT-Sim or through multi-flash, and it is highly dependent on your HTGC distribution for and paraffin HTGC distribution, whereby the wax fraction will be calculated and will be inputted into this software, and your EOS model, equation of state model, in your software will predict the precipitation curve. So here is your wax fraction, okay, or weight percent of your wax versus your temperature, which corresponds to your dC over dt. This one, this is which is this, all right, dC over dt. Okay, and another part is actually your kinetics of your wax deposition. So there's a kinetic model that actually predicts the thickness of wax on your pipeline that will deposit on your pipeline. So they are Olga uses a model which is called the Marzane model, which is quite well known till today. So we are using Olga to predict the amount of wax being deposited on the pipeline. All right. So purpose of models to produce a wax phase envelope to able to detect possibility of wax formation over a range of pressure and temperature, and estimate severity of wax deposition. So models are actually semi-empirical it highly relies on laboratory data to ensure reliable prediction. So it's a, I would say, wax prediction or wax modeling is it's not science per se, it's actually pseudoscience. So it really highly it's an art actually in terms of trying to match the laboratory data, right? Yeah, quite tedious, but yeah. So basically, you need to have certain amount of experience to do wax modeling, because different labs has uh, different way of measuring the data. So some laboratory data is not reliable. So we need to use some. We need to have some. We need to do some engineering judgment and do some assumption to reduce any error in terms of calculating the wax properties. All right. Unlike hydrates is quite well known because the hydrate model is already been validated against multiple experimental data, whereas your wax modeling in terms of prediction, it's really highly it depends on your the waxy nature of your crude. So basically, every fluid or every oil has different wax behavior. All right. So your laboratory data must be as reliable as possible, and the client need to make sure that laboratory conduct the wax measurement properly in the lab. All right. So yeah, this as I've already mentioned. So this is known as a solubility curve or wax precipitation curve. Right? So we need this to be also uh, predicted in the thermodynamic software, and also we need, so once we predict in the thermodynamic software, we need to generate a kind of a table file that will be inputted into your, or that will be inserted into your Olga simulation, right? So yeah, as I mentioned earlier, yeah, this is a DC or DT is your solubility curve. DT or DR is your temperature gradient. Right. There's another term here which is your shear function of this is actually a what do you call it? Shear effect. Yeah, shear effect. But we will not actually in Olga. We'll try. We will just use the default value or in terms of the shear rate. All right, the default value in Olga. We don't do any tuning on that. We only do tuning on the diffusion, the deposition rate. So as you can see here, this is actually a snapshot from Olga, and here is a pipeline, your pipeline length, and this is your wax thickness. So you can see here, here wax being deposited on flow line, and the thickness is about 1.6 mm, and this section is about 0.8 and all. So pigging frequency to predict or to estimate the pigging frequency, or to derive or identify the pigging frequency for your flow line, the rule of thumb that we use is actually we will pick when the wax thickness reach 2 mm. So once your peak reaches 2 mm, that's when we determine the pigging frequency for your flow line. All right. And wax volume at peak receiver as well. Usually it's either 2 mm or 50 barrels. So whichever comes first. All right. If it is if it is 50 barrels comes first, then that will determine your pigging frequency of your pipeline. So frequency is determined by one of or more of these criteria. Significant increase in pressure drop, more than 20% is observed in the field, then we need to be aware that we need to start looking at pigging the line. Maybe there's a solid formation in the flow line. So when there's a big pressure drop, all right. and we pick once 2 mm peak at the wax has built up. So once 2 mm reaches that, but this 2 mm can only can only be that we cannot actually measure uh, on site the 2 mm. It only can be we only can conduct a simulation in order to predict the thickness. We cannot measure the thickness at site. All right, this is through modeling based on wax model and based on wax model. And we pick such that 50 barrels of wax being removed. All right, and we need to maintain the peak pressure drop less than 3 bar. All right, if it is less than 3 bar, that will also determine, that also can be used as a determining factor for your pigging frequency. So better to pick more frequently before it's too late, because if you delay your pigging, your wax tend to get hard, right? It will harden over time, so it will age. So pig is not capable of remove all. So when you pick, if it is too late, then your pig is not able to remove all the wax. And large volume of wax exceeding the pig trap volume if you wait too long. And usually wax is an issue during early life as compared to late life. The reason here is because at late life there will be water breakthrough, and so your water cut will be higher. So your water, since your water cut is higher, so your water will tend to hold more heat, because your of capacity of water is higher, so it can contain more heat. Therefore, you will not foresee any not you will not foresee much wax issue towards the late life of your field. During early field life, yes, that's when your wax will start to wax will be an issue. But it depends whether it depends on the nature of your crude. Yeah, not all of your the whole I mean the whole all of your crude or all field has wax issue. So it depends on the nature of your crude itself. And we can monitor and optimize the pigging frequency based on peak returns. So this is much more better actually in terms of predicting the or determining the pigging frequency. If we have operation data on the amount of wax out being picked for a certain duration or certain time, that will give you an indicative number or indicative or give you an indicative number to determine the pigging frequency for your flow line. If let's say so we need to make sure that operator actually record this wax volume in a spreadsheet for every pigging activity, so that this can be used later on in the wax modeling later on to tune the wax deposition model in Olga. Instead of using cold finger data, this is much more reliable compared to the cold finger data, because the cold finger data, if you notice, is a rotational base flow. All right, so we need to convert that. There's a lot of we need a lot of equations involved for the cold finger data. We need to convert the rotational flow to pipeline flow to axial flow, and then only we can only use that to tune the wax model. Whereas if you have this data, or you have the luxury of getting this data from operation, that would be much better in terms of tuning the model, especially the wax deposition model. So let's look at the mitigation, design and operability issues. So we need to design and to keep the fluid hot by proper insulation or direct heating of the pipeline. Alter the characteristic of wax by blending with less waxy fluid. As I mentioned earlier, we can actually inject condensate and gas, but bear in mind we need to check on asphaltene issue in that case, or using wax or gel inhibition to reduce the wax precipitation tendency. So if, let's say, wax deposition could not be avoided, then we need to quantify the extent of wax buildup to establish the frequency of your wax removal operation. and also remove wax frequently by pigging or melting off, removal by chemicals, and start pigging operations early in the production itself. Allow some insulation to reduce the wax deposition volume. All right, wax deposit volume. So before proceeding further, I would like to actually uh, I got a video for everyone to watch. Let's watch this video together.
Pipelines become blocked when liquids accumulate or wax builds up. Such blockages slow or stop production. Pigging. Pipelines become blocked when liquids accumulate or wax builds up. Such blockages slow or stop production. Pigging clears the line of any blockage without stopping normal production. Knowing how fast to run the pig, when the pig will arrive, and the size of the liquid surge ahead of the pig are critical to preventing an upset in operations due to separator flooding. But how often should a pig be run? Simulation shows how long it takes liquids to reaccumulate, and thus when the next pigging operation should be done. Simulation using the PipeSim simulator to provide steady-state insights, and the Olga simulator to add time-dependent insights enables engineers to define the optimum pig operation to help maximize production.
Right. So basically, if you another thing you have to be aware of is actually if you start pigging frequently, also there will be instability in flow in your production because you will also incur operational induced slugging in your flow line because you will start pushing your fluid to your top to your processing facility. That's when you may also flood your separators, and there will be a fluctuation of production at the same time and water instability at the same time. Therefore, we need to optimize the pigging frequency using a pipe sim or Olga's simulation. As we need to not just look at wax, we also need to look in terms of liquid management, all right, to determine the pigging frequency. I will show you a case study later on. How we actually optimize the pigging frequency for wax and also for liquid buildup, for liquid management. Okay, if gel formation is possible, quantify the time to gel formation to allow procedure established for displacing. So this is when we can actually before this is only applicable when your pipeline is at a shutdown scenario. When your pipeline start to shut down, your temperature profile of your flow line will reduce, or there'll be heat that is heat will be released from your flow line due to the cold ambient temperature. And so basically your pipeline your fluid will actually cool down. Once it cool down, and before it reaches the pour point, we need to displace the fluid in your flow line. Or else if you don't displace, if you keep it remain in your flow line, if it remains in your flow line, then it will gel up the whole section of your flow line. So how do we actually displace is through by displacing from top side using maybe hot oil, or we can also use any displacing fluid or your dead crude. You can actually displace your using dead crude and displace the whole flow line, the whole fluid in your flow line. All right. So do not keep fluid in pipeline during prolonged shutdown. That's if you keep it too long, then there will possibility of gel to form. Okay. And another way is we can inject a PPD, pour point depressant, to reduce the pour point of your crude. And yeah, we have a gel breaking pump here, standby. If in case gel is formed, we can actually break the gel using a pump, which is called a gel breaking pump. All right. But yeah, so basically that's the reason why in the lab we need to have the gel strength being measured as well, because from the gel strength only we can determine the gel breaking pressure of your crude. So the gel breaking pressure, once we obtain the gel breaking pressure, so your pump will be designed for design uh, according to the gel breaking pressure. Insulation, use insulation to ensure arrival fluid temperature is above W80 and sufficient cool down time, and to minimize wax volume returns. And this particular design is very common, and it is only involve high capex, high initial capex, but then there's no opex involved. Potentially difficult to provide sufficient insulation for high WATs due to long tiebacks and also cold environment. In this case, then we need to look at other options, which is through active heating. So localized heating of the pipeline, and it can incur high capex and also opex for your project. We can look at also heat circulation through pipe-in-pipe system, dual pipe configuration, and internal heating circulation, or co-current or counter current. In terms of chemical, we can actually inject chemicals such as wax inhibitors and pour point depressant to manage the wax and also gel. So these chemical injections, right? We cannot actually measure, or no, we cannot actually predict the efficiency of your chemicals using software. So we must depend on the laboratory analysis for the effectiveness of the chemicals that are being used. And all chemicals will behave differently differently according to the nature of your crude. So some chemical can only work well for this type of crude. Some chemical can only work doesn't work well for other parts of the. So basically, one chemical can only work for one particular fluid. It does not necessary that it can work for other fluids. Yeah. So we need to conduct laboratory analysis in order to select the appropriate wax inhibitor or pour point depressant for your specified oil. Okay. So for your oil, and pigging sometimes requires loop flow lines. So pig can start if noticeably there's a pressure drop. Pressure drop is too large across the peak. So that's why we need to maintain the pressure drop across the peak less than 3 bar. All right. And if you don't pick too often, then you might gel up the flow line, and that will incur shutdown to your system and revenue loss. Okay. And we can so for in terms of gel mitigation, when your pipeline is in shutdown scenario, then what you have to do is you have to displace your fluid in your flow line by using a medium such as a dead oil, or we can use also water or other types of mediums, or we can use also hot oil. Yeah? Okay, next let's look at the strategies, mitigation strategies in terms of different operating scenarios. If doing normal operation, the strategy would be to insulate above W80, or we can insulate, or we can heat, or through regular pigging or PPD. So this depends on the severity of your wax deposition. If your wax deposition is too large that that insulation cannot provide sufficient heat retention along the pipeline, then we need to look at heating, and we cannot have if it is too much that heating, and also regular pigging can also be also recommended, but heating would be the better option. All right. Turn down, yes, turn down, your risk for wax deposition will be higher, because when you have turn down rate, when you're flowing at a turn down rate, then your fluid cool down faster. All right, across the flow line, along the flow line. So the strategies would be regular pigging, heating, 4-point depressant injection, or wax inhibitor injection. So during prolonged shutdown, there will be risk of prolonged shutdown. There will be risk of gel formation. So we can the strategy would be to displace the fluid or through flushing. So to start up would be also hot flushing during a warm-up period. All right. Or we can also hit the flow line first. Hit the flow line first before starting up your well. So that's another one more strategy that can be employed in this startup scenario. So we can heat up the flow line above our pour point or above W80, and we can start. Then only we can, once you heat it up already, and we can actually compute the duration of heating using software. So basically that duration of heating, after which we can start flowing the wells. So let's look at this particular case study, which is quite interesting. I was involved in this project back in 2015. So for this particular flow ocean study, there are two objectives. All right. First, the first is in terms of the pigging frequency, we need to optimize the pigging frequency of the flow line. The second one would be to predict the liquid management, or to check for the water slugging, and also the pigging characteristics. So the objective would be to predict the wax deposition tendencies at 3 different flow rates for 3 different pipelines, and recommend the pigging frequency for all 3 pipelines. And in terms of the liquid management, we will predict the liquid water holdup, and to check the water slugging and also the pigging characteristics. So for demonstration purpose, we will only look at one particular flow line, this particular pipeline, and we use this as a case for this presentation. So previously, before we have conducted this study and all, few years before that, this particular flow pipeline faced a very severe gel issue. So they did not pick frequently, and the whole pipeline got gelled, and they need to shut down the field. Okay. And fortunately, this particular pipeline is an onshore field. It's not offshore. So basically, we are able to rejuvenate or revive this pipeline. Or else, if it is offshore, then we need the only way. If there's no means of reviving the flow line, we need to abandon the flow line if it's an offshore field. Since it is onshore, so there's a room for actually to revive and to revive the pipeline. So we don't need to replace the pipeline in this case. So how did they recover this flow line is actually, so along this flow line, what they did was, since the whole section has been gelled up, so it is in the middle of savanna, in the middle of savanna. So what they did was they dug up kind of a dump, a kind of they dug soil, they dug the soil, and they hot tap the pipeline. So they hot tap the pipeline, and so what is hot tap is actually they just puncture into the pipeline, and they inject a hot or inject a steam in order to dissolve the wax. So it will say they hot tap it, and then they inject hot steam. So the oil the oil will actually flow into that pond into that pond. So they sectionalize the hot tapping. So they did it at this section, then they go to this section. So along the 100 kilometers. So they hot tap, hot tap, hot tap. So basically that's how they actually recovered the pipeline. So after which they have came to us, and then they asked us to look at it in terms of they asked us to look at the pigging frequency and stuff. So to determine the pigging frequency for this particular field. So they consulted us, and we came up with this study. Yeah. And also they were also facing some water instability issue, because when they were when they were pigging too frequent, there were a lot of fluctuation in production. There's a sudden water slug. Sudden water slug to this particular field. So for every pigging activity, all right. So there's a lot of instability of water flow that has caused a lot of production deferment as well. So they came to us they asked us to optimize the pigging frequency. Instead of pigging every 2 weeks, they want to try to prolong it a bit longer to avoid the instability of production. At the same time, to avoid any buildup of wax in your flow line. So that's the two main objectives of this study. And you can see this flow rate is about 16,000 barrels of liquid, and operating pressure is about arrival pressure is about 9 bar. Export temperature is 72, but your WAT is about 56.5 degrees C. Right, it's quite high. WAT is quite high. Look at the ambient temperature is only 22. So of course wax will start to precipitate, because there's a very big temperature difference as well. Your ambient is 22, your fluid temperature is 72, and your WAT is about 56.5 degrees C. Okay, water cut is about 5%. Yeah, so this is the property of the wax property of this field for field A. So 56 degrees C, 6.5 degrees C for in terms of WAT. Wax content is about 33.2. It's massive, 33.2. And your pour point is also quite high, which is 33 degrees C. Right? So we conducted the simulation cases. Case 1 based on 22 temperature of 22. These are the flow rates we considered. Right? And develop the wax precipitation curve in a PVT sim or in a thermodynamic software. So this is the amount of wax versus the temperature. Okay, we need this data for the Olga run, right? Olga simulation. And we have also matched the the viscosity below WAT. All right, we match it against the experimental data for the dead oil. And also, so since we do not have the cold finger data, we don't to tune the diffusion coefficient multiplier or DCM for the wax deposition model. What we did was we had the but we have the luxury of operation data in terms of the amount of wax being removed from the flow line through pigging. So we have that data with us. So what we did was we tuned the DCM, the diffusion coefficient, in order to match the amount of wax being removed by the pig based on the field data. All right. So based on DCM of 1, there's a lot of difference. So we try to reduce, then we reduce it to further 0.5. And at the end of the day, we used 0.01. All right, that gives almost a similar prediction. Similar prediction with the with respect to the amount of wax being removed based on field data. This is amount of wax every 2 weeks lah. Every 2 weeks. So let's look at the temperature profile for this field, for this flow line. So this is flowing at 12,000 barrels per day of oil during winter, 22 degrees C. And the WAT is 56.5 degrees C. This black line is actually your temperature profile, and this is your pressure profile. Okay, just this pressure profile is just shouldn't be bad there at all, but just showing that the pressure actually it's flowing downwards. That's why there's a increase in pressure. So the bathymetry is going down. All right. So if you look at this is a temperature WAT, and your ambient is about 22 degrees C. 22 degrees C. So let's draw a straight line here, 22 degrees C. Okay. So your temperature drops to WAT at the first section itself. About 5 kilometers already, it has already reached the WAT. So fluid already reached at WAT. So after which, right, since we have a big temperature difference between the bulk fluid and also the ambient, therefore there will be a lot of therefore the magnitude of the deposition will be high, because the DT over DR is big, the temperature gradient is large. So if you look at it, at the beginning of the pipeline, we will have higher rate of wax deposition. All right. As you move along the pipeline, okay, the deposition rate will reduce, and when at this point here, when your ambient temperature and your fluid temperature reaches equilibrium and there's no temperature gradient, therefore there will not be any deposition on the pipe wall, on the inner pipe wall anymore. The wax will still precipitate, but it will be transported as a slurry instead of depositing on the pipe wall. So as you can see here also, so it is only depositing at the beginning of the pipeline. All right, at the inlet of the pipeline, inlet section. So this is thickness, this is the distance. So the thickness, in terms of thickness, after 14 days is only 0.1. Right? In terms of thickness, it's not much, because it doesn't even reach 2 mm. But then let's look at the volume, or look at the amount of wax being deposited in terms of kilograms. So it's about 200 plus kilograms after 2 weeks, which is a lot, 200 kilograms. So what we can say is actually the wax, for this field, the wax deposition is quite low. So basically, the wax that is being precipitated is actually will remain in the fluid. Right? Then we look at did some sensitive cases in terms of the seasonal effect, which is at different ambient conditions. All right. So basically, of course, at a colder environment, your deposition is higher, deposition rate. Okay. And in terms of so basically, to reach 2 mm, right? To reach 2 mm, it takes about 9 months to reach 2 mm. So we cannot use this criteria in terms of we cannot use this criteria to determine the pigging frequency. So this criteria is no longer applicable for this field. The only criteria we can use now is actually to check the pressure drop across the peak. The pressure drop across the peak, which we need to maintain below 3 bar. All right, that's the criteria that we can use. So look at this is at different flow rates. So at a higher rate, of course, your deposition will be higher. So this is sorry, this should be 8,000, not 6,000. 8,000 and 6,000, right? So let's look at the recommended pigging frequency. So currently they were actually pigging every 2 weeks. Okay. So we did the Olga simulation, and then we checked the peak pressure drop, okay, across the peak. What we notice is that once it only reach above, it only reach a 3 bar when we peak every 4 weeks, right? Every 2 weeks is 1.6. So basically, we are able to prolong the pigging activity with an additional of 2 weeks. So basically, instead of pigging every 2 weeks, we can pick every 4 weeks, and this can actually help in terms of the production fluctuation as well, to manage the water instability. All right, because as you pick, they were picking every 2 weeks initially, and notice that there's a lot of instability in the flow, especially the water instability, and so that has caused a lot of production loss or deferment. So although wax thickness and volume are still small, and pressure drop across the peak increases significantly and is higher than a 3 bar for peaking frequency more than 4 weeks. Okay, more than 4 weeks already higher than 3 bar. The peak frequency can be extended from 2 weeks to 4 weeks to once every 4 weeks for both the season, winter and also summer. Right. So basically, based on this analysis, yes, we actually recommended and proposed operation to extend their pigging frequency from 2 weeks to 4 weeks, right? To avoid any pigging induced slugging, to reduce the pigging induced slugging issue. So let's look at the liquid management side. If you look at the liquid management side, so they were able to decrease the pigging so by decreasing the pigging frequency to once every 4 weeks, it will reduce the duration of water instability by 18%. So that has added value to operation, because this can be in turn can be converted into dollar and cents. So 18%, or we can reduce the water instability by 18% to avoid any to reduce the production deferment, right, and production losses. All right, I think that's all from my side. Arvind, I think I can pass it to you. Thank you everyone for listening to my presentation and also the case study that I've shared. Arvind, I pass the floor to you.
Hi,
Arvind?
thank you so
Yeah,
much,
yeah.
Mr.
Okay.
Dhanaraj.
All right.
Okay,
Thank you.
thank you so much for a very good technical overview of wax management. I think you really went into detail as well. So we learned not only on wax management issues, we also learned on how to actually use softwares for it. Okay, I have four questions, yes, that were posted by the audience. So the first question is, does the Joule Thomson expansion affect the waxy gas condensate pipelines and risers?
Okay, that's a good question. Yeah, Joel Thomson effect. Yeah, that's right. Condensate also can have wax, not just oil. All right. There's a
Okay.
field, one field in Malaysia also has a issue. It's a condensate field, and it's the condensate, but the condensate has also waxy nature. Yes, through Joel Thomson, we can have through the risers, right? You're talking
Yes,
about, yeah.
through the
And
pipelines and the risers.
yes, we have that issue currently in one of the fields in Malaysia for condensate. It's possible that
So it has
wax is formed.
a positive or negative sort of um,
Depends. If you're That's the thing. It depends on the nature of your crude. You need to do some laboratory analysis for
So
the
you get the
condensate,
PVT data first and
data, and then analyze. Yeah, some condensate is waxy, some condensate are not waxy, right? So it depends. We have one field which is, but condensate most condensate is not waxy. It's non-waxy.
okay.
Most condensate is non-waxy.
Is it like a deep water well or
It's a deep water well. Yes,
deep water well?
it's a deep water well.
Okay.
Yeah. So that's
Okay.
non-waxy. What else? Yeah, but then if we were to mix condensate and oil, that will help in terms of the
Condensate
wax.
and oil.
Yeah, mixing of condensate and oil. It will help assist in terms of the wax issue, because your solution gas your gas will help to reduce the wax precipitation or wax WAT, to reduce the WAT, wax appearance temperature.
The second question is it possible if PVT sim, the new data fluid, be imported into Olga?
Pardon? Come again?
The PVT sim new fluid data be imported into Olga?
Yeah, that's what we are doing. We have to
So you
predict.
can import the file, is it?
Yeah, we can import the file. I can show you guys if you have time now. Let me open Olga then. Wait, hold on. Okay, wait. Hold on, yeah. Give me like about 2 minutes. I will open the file. Okay. Open case. Process. Yeah. Okay. Let me share my screen. Can you see, Arvind? Are you able to see?
Put it into stream, but it's not.
Okay.
No.
Can you see now?
Yes, can view it now.
Okay, cool. So if you look at this, right? Okay, let's look at the files here. All right. Library. So here, files, all these files here. So here we can input the wax file. Here, wax file, and this is your PVT file, all right? And then in terms of the modeling, right? You want to have a look at, okay, wax. So here we can actually specify this is a wax table. Okay, this wax
we can create all the fluid in PVT sim and then just import it into Olga.
Yes, that's right. Then you look at this. This is a wax table, right? This is your actually your wax precipitation curves and all, right?
Yes.
Right.
Yes.
And then your DEF is actually your for your viscosity.
Correct.
Remember the DF? Yeah.
Correct.
This is to take into account on the wax, the waxy nature of your for the viscosity lah.
All
W80
right.
prediction of the viscosity below W80. So these are the multipliers that we need to input, and it is only can be obtained through PVT sim. Right?
Is it a fixed default multiplier that you need to,
The default
or
is
does it
one.
depend on your field?
Depends on the fields.
This is a
Depends on
viscosity prediction model.
this is the viscosity prediction model. All right. Which
Based
is
on
the
wax appearance temperature.
based on the wax appearance temperature, which is this one. Wait. Hold on. Yeah. This one. Yeah. Look at this. You look this one.
Okay.
So basically, if let's say your wax is there's no wax, so this property will be this one will be 0, 0, 0, right? So
Yes.
exponent of 0 is 1.
Yeah.
So your fluid will be just will not depend on the wax. Will not depend on the wax.
Okay.
Right. So this, and we need to get these multipliers lah. It can be these multipliers need to be tuned in PVT sim.
Okay.
That's when so you input this here. This is a wax table, and the wax and also the wax files will be included here. This is the fluid file. The fluid file from PVT sim, and this is the wax file. Yeah. And another thing is that you need to tune. In this case, I've used default of 1, the diffusion coefficient multiplier.
Yeah.
So this one we can be
Usually
tuned.
the default is 1. Yeah.
Yeah, default is 1. But for this particular field, if you look at it, I've used I've used 0.01.
Okay. How come?
Yeah. Because I'm trying to match the field data in terms of the amount of wax being removed. So basically, if I use 1, my model is predicting like 10,000 kilograms, whereas versus the field data is about only like 200 plus. So I've reduced it further. I reduced the DCM and ran the simulation again. So there's a lot of sensitivity analysis done here until I reach a point where I could match the field data.
Field data. Okay.
Which is about 2.
So you just modify the coefficient so that you can match the field data. Okay.
Yes, correct. I just modify the coefficient to match the field data.
Okay.
Okay.
All right. Thank you.
No problem.
Okay. I have another 2 more questions. Just bear with me. The next question is, what is the major difference? This is posted by one of our students. So what is the major difference of between when we talk about pour point and WAT? The
Major
difference, yeah.
Okay, as I mentioned earlier.
Physical difference?
Oh, physical difference.
Yes.
Physical difference. Okay, if you look at physical difference, pour point, when your crude goes to pour point, that's when your crude will be in solid phase. That means the whole crude will be like a solid phase. It will cease to flow. So it will form. It will be like a gel.
Gel strength will be very strong.
Yeah, gel strength will be strong, and it will be like a gel, like a solid.
Okay.
But WAT, when you are operating below WAT and it is above pour point,
okay,
your fluid will be viscous. It will be viscous, but it's still flowing. It will be flowing.
Okay.
Just that pour point, when you operate below pour point, then your production will cease to flow lah.
Yes.
Because gel is formed. Yeah.
All right. The last question: does cloud point and pour point mean the same thing?
No, it's different. Cloud point is it's when it's visually you can see that
I
there's
think
a,
usually in terms of academia side, we don't really use cloud point. I mean, we don't use the term cloud point, but usually in the industry they do.
yeah, they use
So
cloud point, but
yeah,
we don't use cloud point to do our we don't use cloud point
to run
to do our modeling,
simulation or
to
prediction
run
model. Yeah,
simulation. Only WAT. So the
yeah.
cloud point is actually the first crystal that's formed, and you can see a cloud, kind of a
It
cloudy.
doesn't matter whether it is microcrystal or macrocrystals, right?
It doesn't matter. Doesn't matter whether it's micro or micro crystal. Yeah. So if you look at the definition of cloud point and WAT, let's look at that again.
I think they're very much
So
similar.
they are very much similar,
Mm.
but in terms of measurement, in, for modeling purpose, we use the WAT to do the matching, right? Not the cloud point. Okay. So it just give an
WAT instead
indication
of
for
cloud.
potential wax problem only,
Okay.
and does not represent on the
But
onset
usually
of.
when they run prediction models, they usually use WAT because that will give a better. I mean, you can also use that in terms of doing Sarah analysis and stuff.
Yeah, yeah, yeah.
Okay.
But Sarah analysis is only used for asphalting study.
Yeah. Asphaltene and resins usually.
Yeah, acidity and resin,
Yeah.
aromatics and
Yeah.
resins, correct.
Because that one actually contributes towards wax, if I'm not mistaken.
Contributes towards the
Wax
instability.
deposition, right?
No, no, the Sarah is for the asphalting.
Asphaltene,
So
sorry.
so basically your it if you it is stabilized by your resins, your asphalting is stabilized by the resins.
Resins.
So if you start injecting gas into the oil, it will destabilize the nature of your
Ah,
resins and asphaltene. That's when asphaltene will start to precipitate lah. So
precipitate.
Sarah analysis is only done for asphaltene study, right? For
Asphaltenes.
asphaltene
Okay.
study.
Okay, so those were the four questions that I had. Nothing more from the audience. Um, we would like to thank you, Mr. Dhanaraj, for
All right,
providing us with so much of technical knowledge.
all right.
And we
Thank you.
hope to actually get you engaged more in terms of more webinars in the future.
All
So
right, sure.
thank you very much. Thank you very much, and thank you everyone for actually tuning in on a Sunday. And we hope you enjoy the rest of the weekend. And see you back in office. Take care.
Okay, take care.
Stay safe.
Thanks everyone.
Bye.
Stay safe. Bye.
Bye.